Hello class, welcome to this video on the EOC review practice. So this is part 2 of the three-part series. So we're going to cover the next 12 to 13 pages of the guide. So let's go ahead and get started. So the first standard for this part is construct an equilateral triangle, square, or hexagon in a circle, inscribed in a circle. So Carolina wanted to construct a polygon inscribed in a circle by paper folding. She completed the following steps. So she started with a paper fold, she folded it in half, made a crease, she takes the half circle and fold it in thirds, and then crease along the sides of the thirds. Open the paper, mark the intersection points of the creases within the circle, and then connect adjacent points on the circle with segments. So she took her paper fold, she folded it in half, so she got something like that. Then she folded that into thirds, and so when she does that, she ended up getting, so this gets folded into thirds, and so this goes into the other half as well because it's folded. And so you got these creases, she marks these points here, and lo and behold, if you connect these, you can actually get a hexagon out of it. And so this is how she was able to construct a regular hexagon. Okay. Number 2, Carol is constructing an equilateral triangle with P and R being two of the vertices. She's going to use a compass to draw circles around P and R. What should the radius of these circles be? Okay, so she's going to use her compass to draw. So she's going to basically, need a point here so that she can make an equilateral triangle. Now, if it's equilateral, that means these distances have to be the same, all of these distances. And so they all have to be a distance of D, right? Which is that top part. And so basically she needs to set the compass so that it is at a width of D so that she can make some circular arcs on either side of this. So yeah, the width of the compass has to be D in order to mark those arcs so that we can get a nice equilateral triangle. This is going to be A. All right. Dea is drawing a square inscribed in a circle using a compass and a straight edge. Her first 2 steps are shown below. So she's got these two. So she got her 2 steps there. What is the next step for her to do? So step 3. So remember that when you're drawing a square inscribed, you need to draw a diameter. So by picking a point and then use a straight edge, which is step 2, right? And then you need to draw another diagonal that is perpendicular to that. And so in order to do that, you're going to need to, all right, so in order to actually do this, we're going to need to basically construct a perpendicular bisector here that cuts this in half. And so to do that, you're going to need to mark a couple arcs here and here so that you can cut this in half. And you're going to mark it with the compass so that the width of the compass is a little bit more than half of the distance, half of the halfway point, a little bit more than the halfway point, and then you can draw your arcs above and below in order to make your perpendicular bisector. And these are the arcs that you're created, and then you can connect those for the final step, and then continue from there to make your square, because then you'll end up connecting these points for the final step. Okay, so the next step is to make that perpendicular diagonal there. So that's going to be D. Okay, so for number 2, or for the next standard rather, has to do with dilations and scale factors. So a line that passes through the points whose coordinates are 1, 1, and 5, 7 is dilated by a scale factor of 3 and centered at the origin, the image of the line. Okay, so here we have a line, just any line. Let's go ahead and draw the line. We got 1, 1. And 5, 7. Okay, so there's our good old line, and we want to do a dilation. We want to dilate it by a scale factor of 3. Well, if we about the origin, so we're going to do it here. So, well, if we did that, basically this will be 3 times as large, and so you're going to end up stretching this out 3 times as big. So let's show you how we would do this for this example. Well, then I would have to figure out, okay, well, what's the distance between the origin and this point? And then I would multiply by 3, basically. So if I want to scale factor by 3, then I just got to multiply everything by 3. So this is going to be, if I multiply 1, 1 by 3, I get 3, 3. If I multiply 5, 7 by 3, both coordinates, I get 15 and 21. 7 times 3 and then 5 times 3. So I would get 3, 3, you know, somewhere around here. And then I would get 15, 21, which is all the way over here and all the way up here, right? And so what you'll see is that the lines are going to be parallel, but they're not going to be the same line. This one's going to be longer than the blue one. It's going to be 3 times as large because the scale factor is 3, but it's going to be parallel. So the answer is B. All right, in the diagram below, CD is the image of AB after a dilation of scale factor K with center E. Which ratio is equal to the scale factor of the dilation? Okay, so remember, so this is the center of dilation. So what you do is, and so this is the pre-image. No, this is the image, rather. They said CD is the image, so that's the image, and this is the pre-image. So what that means, it shrunk, it got smaller. So you're going to go from the center of dilation straight to the pre-image, right? And so you need to figure out that distance. So the scale factor is always equal to the image divided by the pre-image. Okay, so the image here is EC. And then you divide that by the pre-image, which is EA. So in this case, that is your scale factor, is EC over EA, which is going to be A here. Okay, so that's always how you do the scale factor, is always image divided by pre-image. All right, so the vertices of square ABCD are those given there in those coordinates. This square is dilated so that A prime is at 3, 1, C prime is at 8, negative 4. So it's best to actually draw this out so you can kind of visualize it. So we'll take a bunch of this space so we can draw it out. Okay, so we have here so these are going by 1s here. Okay, so let's go ahead and draw this out. I wanted to space it out so that we have enough space to kind of illustrate this. So the original is 3, 1, and so that's point A. Then you got point B is 3, negative 1. Point C is 5, negative 1, and point D is 5, 1. All right, so there's my original square. Now we want to dilate it, so A prime is at 3, 1. So A prime is actually at the same spot that A is, which means that the dilation is occurring from this point and then it's getting stretched. Okay, so it says A prime is at 3, 1 and C prime is at 8, negative 4. So the C prime is at 8, negative 4. So this is going to be C prime. So notice that I'm stretching this out so that it looks like that, right? And so that's going to be my new image, the red. And so basically I have to stretch this out. Well, this is at a distance of 8 and it's starting at 3. And the distance here is 2. So it's going from 2 to a distance, and then let's see here, is it from 5 to 8? Yeah, so this is actually 3. So this is a total of 5. So basically it's a 5 by 5 square. But in other words, you can kind of tell that this is going to be D prime. So D prime is going to be at 8, 1. So there you go. Picture's worth 1,000 words here. You can definitely tell that it's going to be at 8, 1 for D prime. All right, so for number 4, GH is 1. A dilation with center H and a scale factor 0.5 is applied. What will be the length of the image? So we'll just draw it out. So GH is equal, that length is 1. and a dilation with center H, so that's my center there, and you're just stretching it, or you're actually compressing it by 0.5. So really, it's just going to be from here to there. That's 0.5. So half. This is half. So half of 1 is half. So the length of this is still going to be just half. So that one's actually pretty trivial. If this were a length of 2, then this would be half of 2, and it would be 1 in that case, right? So that's all you have to do there. So for this one, the next standard, we're talking about similarity and similarity transformations. So for number 1 in the diagram below, you have 2 triangles. AB is 6, AC is 8. Which statement will justify similarity by SAS? Well, okay, so let's see which is going to be true here for SAS, will justify it. Well, let's look at the first one. If DE is 9 and DF is 12, angle A is congruent to angle D. So let's see if this is going to be similar by SAS. Well, we got that the angles is the same, so that's check, right? So now we need to look at to see if the sides are proportional. So 6 is to 9 as 8 is to 12. So let's see if that's true, okay? So 6 is to 9 as 8 is to 12. Is that true? Well, if we cross multiply, do we get the same thing? Well, if we cross multiply, we get 72 is equal to 72. So yes, these are proportional. So we have side, angle, side, side, angle, side. So yes, this right here, this is going to be correct. This statement is going to justify similarity by SAS. And so we're good. So it's A. Number 2, in the diagram below, triangles XYZ and UVZ are drawn such that the angle X is congruent to angle U. XZY is congruent. So XZY, so that's this angle, is congruent to that angle. Describe a sequence of similarity transformations that shows that the triangle on top is similar to the triangle on the bottom. Okay, well, there's a couple of things that you could do here, but here's an example of what you could do to transform this. You could take this triangle and you can rotate it by a certain angle. If you did do that, then you would notice that the Y here would be kind of over here where the V is on that same side. The X will be moved to where this U side is, and the Z will stay the same because we're rotating it about that point there. So we're rotating it about point Z, and so you'll get something that looks like that. And then at that point, you can do a stretch and stretch it out so that it fits the shape. You could stretch it by a factor of 2 because it looks like you could fit 2 of these sides onto one side. So there you go. So we could do a rotation by a certain angle, let's call it angle theta, about point Z, followed by a dilation that looks to be approximately by 2 about point Z. And there's my sequence of transformations. You could just describe it and say there's a rotation about Z, followed by a dilation of factor 2 about point Z, or centered at Z. You would have to say centered at Z. And there you go. You just do a little description to show that, you know, they'll end up overlapping if you did that. Okay, so for the next question, it's supposed to say when are two triangles considered, or when are two triangles considered similar but not congruent? So let's see here, similar but not congruent. So similarity means, you know, when you're looking at two triangles, is that the sides are proportional. So like this side is proportional, you know, those sides are proportional, you know, to say these, right? So there's proportionality there. They're proportionate. So for example, if the proportions of this triangle are, you know, 2, 3, and the proportions of this one are 6, 9, well, these are the same. These are the same proportions because, you know, I can just multiply this by 3 and get 6, and multiply that by 3 and get 9. So they can scale to get from one to the other, right? So we're talking about scaling. So the distance between the vertices are equal? No, These red ones are not the same distance. The distance between corresponding vertices are proportionate, yes. Okay. For number 4, the vertices of triangle JKL are given. Find the coordinate pairs of the vertices for each of the dilations with a scale factor of 5. Okay, so we want to dilate about the origin. So if I want to dilate about the origin, I simply have to multiply the x and the y coordinate by the scale factor. We'll call it n. So if I want to convert the -3, -2, then all I got to do is multiply that by the scale factor. The scale factor here is a scale factor of 5, right? So this is going to be d5. So it's going to be this times 5, and then -2 times 5. So then the answer is going to be j prime is going to be -15 and -10. Pretty straightforward. And then for k is going to turn into 5 times 1 is 5, 5 times 4 is 20. There you go, that takes care of that one. And then finally we got for 2, this is for d5. You got to do 5 times 4 is 20, and then 5 times 2 is 10. Okay, so now let's talk about dilation about a arbitrary point. So this time we're dilating about point J. So in order to do this, it's better for me to kind of draw it out and show you. Okay, so we'll draw this out real quick, and so we'll try to draw the triangle. Okay, so we know that J is -3, 2. That's J. We know that K is 1, 4. And we know that L is 4, 2. Okay, so we know that much. And we're dilating about point J. So we're doing a dilation of 5, but this time about point J. So we need to figure out, if I want to do it about J here, then I need to figure out how long JL is and how long JK is and how long KL is, and then multiply those distances by 5, okay? So in order to do that, I got to find the x and the y distance. So the x distance is horizontal distance, is the distance from -3 to 4, which is 7. Then I got to find this vertical distance from -2, that's the y value of -2 here, to this y value, which is 2. From -2 to 2, that's 4, a distance of 4. Okay, so now I got those distances, and I got to multiply each of those distances by 5, because that's my scale factor. So I got to times that by 5, I get 35. Times that by 5, I get 20. Okay, so those are my scale factors. Next, I'm going to do it for JK. So if I go up about from -2 to 4, that's 6 spaces. And then from -3 to, this is 1 right here, is 4 spaces. So 6 and 4, and then I multiply each of those by the scale factor. That'll give me 20 there and 30 up here. And then finally we'll do it for KL. So it's going to be from 1 to 4 is 3 spaces, and then going down from 4 to 2 is 2 spaces. Multiply them by 5 to get 10 here. 15 here. Okay, so now let's do JL. So if I want to figure out where the new coordinate is for, from J to L, I need to get my coordinates of J. The coordinates of J are -3, 2. And I need to add 35 to the x coordinate and add 20 to the y coordinate. Okay, and that's going to give me my new coordinate. So we'll call it J prime. Okay, so my J prime is going to be the original J coordinate plus 35. And then the original J coordinate plus 20. Oh, I'm sorry. Sorry, I made a little mistake there. My original J prime is still going to stay there. Sorry, J prime is going to stay there. Nothing's going to happen to it. We're talking about L prime. L prime is going to change. So J prime will stay the same coordinate because we're stretching it from there. So J prime is pretty easy to do. Now, L prime, in order to get L prime, I got to add to j. Okay, so I got to do -3 and then plus 35 and then 2 plus 20. And that will be where my new L is going to be. And so my L prime is going to be 32 and 22. Let's see here. Hold on a second. We'll make sure I got the math right. Okay, so that looks about right. And then for K prime, I'm going to take my original J, right, the -3, -2. This should be a -2. I apologize. I did make a mistake there. So then this is 32 and 18, because that should be a -2 for J. Okay, so -3 plus 35, or not 35. For K, we gotta go. Yeah, it turns out we didn't really need this part after all. We only needed the JK part. So we're gonna go up 30 and over 20, right? So yeah, up 30 and over 20. So we're gonna add 20 to the -3 and add 30 to the y coordinate. And there you go. All right, so then my K prime, sorry for the writing here, it's going to be 17 and 32. All right, and those are my coordinates. So that's how you do it when you're trying to stretch about a point. You got to figure out the distance from that point to each of the other points, and then multiply by the scale factor, and then add to the original coordinates accordingly. All right, so that takes care of that problem. So let's look at the next standard. Use the properties of similarity transformations to establish AA criterion for two triangles to be similar. Okay, so is triangle ABC similar to triangle ADE, and justify your answer? And the answer is yes, they are similar, and we'll show you why that's the case. Well, first off, we note that this angle right here is congruent to this angle. So we know that angle B is congruent to angle D. We also note that this angle right here is congruent to itself. It's congruent to itself because we're talking about this triangle and then we're talking about this big triangle, right? And so they share that angle. And because they share that angle, that means it obviously is equal to itself. So angle A is congruent to angle A, and this is by reflexive property. And this is given to us, right? That was given in the diagram. All right, and we also know, and so therefore, because we know those two angles, that must mean that this third angle, right, has to be congruent here. And that's because, if we know that the other two angles are congruent, then that must mean that that third angle must be congruent. And so therefore the triangles are similar. So these triangles are similar by AA, by AA similarity. Okay, so triangle ABC is similar to triangle ADE. How do I know it's in that order? Well, because I got AB is from the single arc to the double arc. AD is from the single arc to the double arc as well. And so that's AD. And BC is to DE, right? BC is this from the single arc to the triple arc. And and then DE is from the single arc to the triple arc. Okay, so that's in that order. So they're similar by angle-angle similarity theorem because the two angles are congruent. All right, so that's the AA similarity theorem. So let's do number 2. Which facts allow you to prove that the triangles are similar by angle-angle similarity theorem? Okay, so let's take a look at the answer choices there. So it says all right angles are congruent and angle C is congruent to angle C. Okay, so angle C is congruent to itself. That's what they're saying there. And all right angles are congruent. Is that going to help us with angle-angle similarity? Well, first off, remember that we're talking about ABC, as well as CBD. So let's color code that. So those two angles there. Okay, so notice that we're looking at, okay, well, we're saying that these two right angles are equal. That's okay, these two blue right angles. And it also says that angle C is congruent to angle C. That's not going to really help us prove that, because they don't even share that angle. This purple triangle does not even share that this blue angle with the red triangle. So we're going to ignore that. So we're going to cross that out. All right angles are congruent, and angle A is congruent to angle B. Angle A is congruent to angle B. So if we were to know that, it says which facts allow you to prove it. So if we were to know that fact, well then now we have an angle, and we have this right angle as well. So then we could say that these two triangles are definitely congruent by angle-angle similarity. So yes, this is the right application of angle-angle similarity. However, now that I think about it, if you look at the diagram, or if you look at, we want to prove, so this, even though this will help you with angle-angle similarity, this statement right here is actually going to prove that some other sides are congruent. So for example, for this similarity statement, this says ABC, it has to be similar to CBD in that order. And so that means that A has to be congruent to C, and B has to be congruent to B, and C has to be congruent to D. So if you look at this statement here, it says that A is congruent to B. But in this case, A is not congruent to B. A is actually congruent to C. And so this statement that A is congruent to B is not going to show, it's not going to help us prove this similarity statement. It'll help us prove another similarity statement, but not that statement. So this one's a little tricky. That one is actually an angle-angle similarity, but it's not the right one that we want. Okay, so let me erase this, and I'll try to redraw this because it's going to be kind of confusing with all these things going on. Okay, so all right angles are congruent, these two blue angles, and angle B is congruent to angle B. So if we said that angle B is congruent to angle B, it's congruent to itself. And so now you can see that these two triangles share that angle, and we can show that this is an angle-angle similarity case. And not only that, if we were to look at these angles, well, we know that since B is congruent to B, that's true here. And we know that if I were to transform this purple one, it'll actually line up with C. If I take D and kind of flip it around, right, or kind of, I guess you could say kind of flip it and then rotate it, then it will kind of line up with, so that D lines up with C. And it'll kind of look like, it looks a little odd, but it'll kind of look like that, right? Like that. And so that's C, right? And then this right here is going to be like your D. So you have CD, and so this will be B. And so you can kind of see that these two triangles are similar. CB is to, if you go here, CB is to, or rather AB, sorry, is to CB. And then BC is to BD, which is the case here. BD is to BC. So this is the right statement, so it's going to be C. All right, so for number 3, complete the proof below by selecting the correct statement. All right, so we're given that so we're given these things here. So we're given that AB is parallel to DE. We're also, this is not really giving us much information. It's just saying that they're there, that they exist. So we want to prove that DC over BC equals DE over BA. Okay, so let's go ahead and look at the statements here. So let's select the correct statement. All right, so we have AB is parallel to DE, and that's given. Angle D is congruent to angle B. Angle A is congruent to angle E. So A is congruent to E, and that's true. and D is congruent to B, and that's true. And that's true because since these are parallel lines, these two angles are alternate interior angles, and alternate interior angles must be congruent. That's the alternate interior angles theorem. All right, and then so now that we know that we have two angles that are the same, and then that means we can show that these two triangles are congruent or similar by angle-angle similarity. Okay, so more specifically, which ones are similar? Well, we know that these are congruent. These angles are congruent because of vertical angles. And so the way we can set it up is, let's look to see which ones correspond to one another. So if we look at triangle, let's look at triangle ABD, or ABC, sorry, the one on the bottom. So AC corresponds to, AC is between the first and the triple arc, and so we want to go between the first and the triple arc. So AC corresponds to EC. So AC corresponds to EC, so we got to put it in that order. And then BC corresponds to the two between the 2 and the 3 arcs, and so that corresponds to DC. So BC and DC, and that's the order in which it goes. ABC is similar to EDC. And so the answer is C. ABC is the same thing as EDC, or DEC. If I swap these, DEC, then I can swap this and make it BAC. So they mean the same thing. So the answer is C. All right, so for the next standard, we want to prove theorems about triangles. So for number 1, so it says find the perimeter of ABHG, round your answer to the nearest hundredth. Okay, so first off, what we want to do is, this is a ladder theorem. So we want to use the ladder theorem, and the ladder theorem states that if you have a, like a ladder kind of, shape here where it looks like a ladder, then A is to B as C is to D. So you could set up a proportion like that. Okay, and that's the ladder theorem. Here we have multiple rungs on that ladder, but you could still do the same thing. It's still going to hold true. Okay, so what we're going to do is we're going to try to find y. If I want to find y, well, I'm going to trickily use, I'm going to use this one, I'm going to use this side. I'm going to say that 12 is to 21 as 15 is to y, and that's using the ladder theorem. And then I can cross multiply to solve for y. All right, so that's going to be 12 times y equals 21 times 15 is 315. Then I can divide by 12, and I get y equals 26.25. So now we got our y. And that means that this here has to be equal to 12.25 if I subtract 26.25 minus 14. All right, so now let's go ahead and get x. So I'm going to say that, so this time I'm going to be using 12 is to x as 15 is to 10. So 12 is to x as 15 is to 10. You can use any combination for the ladder theorem as long as they correspond on the same side. So then cross multiply, we get 15x equals 120. Divide by 15 on both sides to get x. X is equal to 8. And so now that we know x is 8, we can say that that's 8. And then we can plug 8 into there. 5 times 8 minus 3 is 37. Then we can find the perimeter by adding up all of the sides. So we add up 12 plus 21 plus 8, which is that left side. We add 37, this bottom side. We add up this right side, 15 plus 26.25 plus 10. And then finally we add this top side, 12.25. And we get a perimeter of 141.50 inches. Okay, so it says given EP is equal to FP and GQ is equal to FQ, what is the perimeter of triangle EFG? Okay, so if we want to do this, if we want to get PQ or any of these and solve for x and y, there's one theorem that we want to use, and that is known as the triangle midsegment theorem. Now, the triangle midsegment theorem states that if you have a triangle and then you have a line that connects the two midpoints of the sides of the triangle, and this side is parallel to the base of the triangle, then this midsegment is half of the length of this one on the bottom. So if this one on the bottom is 10, then this one on the top will be 5. Okay, so that's the triangle midsegment theorem. And we know that that's the case because it says EP is equal to FP, and these are equal to each other. And so this must be connecting the midpoints of those two sides, and therefore the triangle midsegment theorem. Okay, so we know that this x plus 2y has to be half of whatever this side is. Let's call that side z. So x plus 2y must be half of z. So z divided by 2. And I'll actually write it as half of z. Okay, so we need to find z or any of these other two sides, and then we'll plug it in. So we're going to use that later. We're going to tuck it away for later. Now we also know that since these are equal, we can set them equal to each other. So we have 3x minus 1 is equal to 4y plus 4. Those are equal to each other. And they also told us that 2x is equal to 4y plus 2. Okay, so we got a system of equations. What I'm going to do is I'm going to divide this by 2, and then that'll give me x in terms of y. So 4 divided by 2 is 2, so we get 2y plus 1. And then we can plug in for x. We can plug this in for x into here. And if we do that, we get 3 times x is now 2y plus 1 minus 1 equals 4y plus 4. We can distribute. We have 6y plus 3 minus 1 equals 4y plus 4. This is going to be 2. So we got 6y plus 2 equals 4y plus 4. I'm going to subtract the 4y on both sides here. You got 2y plus 2 equals 4. So that means 2y has to be 2, which means y has to be 1. All right, finally we got y, and then we can plug this in to get x. 2 times 1 plus 1 is 3. So now we got x and y. Okay, so then we can plug them both in. So this and this can be plugged into here. So we get 3 plus 2 times 1 has to be half of z. 3 plus 2 is 5. So that means z has to be 10 because 10 divided by 2 is 5. So z is 10. Okay, so we now got all the sides. This is 10. Y is 1. So this is going to be 4 times 1 plus 4, which is 8. So that's 8, and this is 8. And we know that x is 3, so 2 times 3 is 6. So that's 6, and this is 6. So we can add up all the sides and finally get the perimeter. So the perimeter is 6 plus 6 for that left side, 10 for the bottom, 8 plus 8 for the right-hand side, for a total perimeter of 38. So the problem's very involved, but we have found all the variables, and then we found the perimeter. So for number 3, we want to find BD, so we want to figure out this side. There is a theorem that states that if you have an angle bisector, which that's what this is an angle bisector, it's cutting that angle in half. So if you have an angle bisector, well then A is to B as C is to D. So you can use that proportionality. That's a theorem that you can use. So we're going to use that theorem here. We're going to say that x is to x plus 5 as 12 is to 27. So x is to x plus 5 as 12 is to 27. And then we can cross multiply. So we'll cross multiply here. We got 12 times x plus 5 equals 27x. Distribute. And we'll subtract 12x on both sides here. Divide by 25. or that should be 15, not 25. So x is equal to 4. And so now you know x is 4, so that means this has to be 4, and this has to be 9, and so BD is 4 plus 9, which is 13. All right, so looking at the next question, number 4, a diagram from a proof of the Pythagorean Theorem is shown. Which statement would not be used in the proof? Okay, so the proof of the Pythagorean Theorem using similarity can be a little bit interesting in that it's a little bit involved, but let's go ahead and use it. So in this triangle right here, we know that triangle BAC, this big triangle here, is similar to triangle BDA. And the way I know that is because this is the right angle. Well, this is a right angle. And this right here is congruent to this right here, and this right here is congruent to that. So we can use that to help us assign which ones are similar. So we know that triangle BAC is similar to the purple one, triangle BDA, and which is similar to, and we'll outline the red one. The red one is ADC, this one right here, which is similar to triangle ADC. Okay, and you can tell that that's the case because you're going from, this is a right angle, from a single arc to a right angle, single arc to a right angle, BD and AD, BD and AD, and then you're going from a right angle to a double arc, which is DC, right angle to a double arc, DA, DA, DC. So that makes sense, okay? All right, so we know that that's true now. So now that we know that that's true, we're going to see if this is going to help us with the theorem. So we know it says AB squared plus AC squared equals all of this. So we got a bunch of stuff going on. We'll talk about that in a little bit. First off, we know that this is true. So because we just wrote it down. So that is true. They're asking for what is not in the proof, right? So that means that this is not the answer because that is actually part of the proof. We're going to actually use that. Okay. So because this is true, right? Let's see if we can use this part C here. Well, AB has to do with, so AB is to, so let's look at it over here. So AB is to BC. So AB is to BC as BD is to AB. And you can kind of see that using that pattern, right? Those are related to each other. Okay, so AB is to BC as BD is to AB. Or, yeah, AB. And then if we cross multiply that, you're going to get AB squared is equal to BC times BD. All right, and similarly, we can cross multiply this, and we get AC squared equals BC times DC. All right, so that's how we get that. Now, how do we use it? Well, we use that in part NA. So we use that in here. So we know that from the Pythagorean theorem, AB squared plus AC squared is equal to BC squared, right? So let's go and write it out. AB squared plus BC squared is equal to, sorry, I wrote down the wrong order. AB squared plus AC squared is BC squared. Okay, now we know that AB is all of this, right? So I can replace that. So that's exactly what I'm going to do. So I'm going to say that, so I'm going to go ahead and replace this right here with that. So we get, that gets replaced with BC times BD. And we also know that this AC is going to get replaced with BC times DC. All right, so now what we're going to do is we're going to factor out the BC. We're just going to pull that out. And if we do that, we get BD plus DC. And notice that this is actually equal to BC because BC is BD plus DC. And that's equal to BC. So therefore, this is actually BC times BC, which is BC squared. So this does check out from the Pythagorean theorem. So that's how you prove the Pythagorean theorem is true, by using those proportions. So that means you're going to use this for the proof, so you're not going to be saying that that's the answer. You're going to be using that for the proof. The only thing that you don't use for the proof is D, the fact that it's a right triangle with an altitude of AD. You don't really use that because this is not even an altitude that you're looking at. All right, so that is the answer. That is the statement that will not be used in the Pythagorean theorem. Okay, so let's look at the next standard. Use congruence and similarity criteria for triangles. So select all the true statements for number 1. Okay, so for this one, we want to see, is ABC congruent to DEC by SAS? Let's see if that's true. So ABC is this one, and DEC is this one. All right, so we got a side, and we got an angle. And that is all we have. We don't have anything else in this between these two triangles, so we cannot prove similar congruence by that. So that's not true. ABC is congruent to DEC by SSS. So ABC, DEC, so the same triangles, S, S, A. We only have S and A. We don't have anything else, so I'm not going to choose that one at all. All right, so AFC is congruent to DFC. So AFC, DFC. Okay, so for those two triangles, we have a side and an angle, side and an angle. We know that that's 90 degrees because they add up to 180 because of linear pairs, supplementary angles. So we only have an angle and a side. We have nothing else. So it's not going to be angle, angle, side. However, we do know that these are right triangles, so we can think of this as a hypotenuse, which it is, and an angle, and a leg, right? We actually do know something else now that I think about it. We have the angle, we have this side, and we do have this side right here, right? The side that they share in the middle. So that's going to be, we're going to call that a leg, because that is a leg, and this is a hypotenuse, right, for the right triangle. So we do know that if you have a right triangle and you know the hypotenuse and the leg, then the two triangles are congruent. So this is true by HL. All right, so we talked a little bit about HL and those other theorems. Let's look at this one here. It says, based on the angle measures in the diagram, what is the measure in degrees of angle N? So since we know that these are congruent because it says it there, we know that angle J must be congruent to angle O. And so if this is 60, then this must be 60 degrees. And therefore, we can figure out what angle L is. And similarly, we know that angle K is equal to angle N, and not angle K. Angle M is congruent to angle L, and if M is 56, then L has to be 56. So therefore, if you want to get angle N, you just have to use a triangle angle sum theorem. These three angles have to add up to 180. So the measure of angle N plus 56 plus 60 is equal to 180. So you just subtract them from 180. And you get the angle N is 64 degrees. All right. So for number 3, what is WZ? So for this one, we're going to use similar triangles to help us out here. This one's a little different. There's a few steps that you got to go through. So first off, what we're going to do is let's go ahead and label some of these. Let's call this Y, let's call this Z. And let's see here. And let's call this X. So we have X, Y, and Z. actually, let's call this x. And hold on a second. Let's see. Let me try to get my variable straight here. Yeah, let's just call this w. Okay, so we got w, x, y, and z. Okay, so let's go ahead and get w here. So if I wanted to get w by similar triangles, I know that I can say that 6 is to, so we can use one of the theorems that 6 is to 4 as 3 is to w. So we're going to be using that theorem. 6 is to 4 as 3 is to w. And then you cross multiply, you get 6w is equal to 12, so that means w is 2. Okay, so now we know w is 2. And then what we're going to do is we're going to use that fact in order to help us find, you know, some of these other sides on the right triangle. Okay, so let's go ahead and get y. Let's get y. So we know that 9 is to 6, or 9 is to 6 as y is to... so we know that 9 is to 6. We'll write it out here. 9 is to 6 as this side, which is now 2 plus 3, which is 5. So now that we know that that's 2, that means this is 5. So 9 is to 6 as x is to 5. And x is that whole side. And then you can cross multiply, and that'll give you the entire side x. So you get 6x equals to 45. Divide by 6 on both sides, and you get that x is 7.5. Okay, so I think they want us to find wz. So they want us to find z, basically, and what I labeled z. So next what we're going to do is we're going to try to find y, and then subtract that from x to get z. So we're going to try to find y here. So in order to do that, okay, so now that we got x, what we're going to do is we know that we can get, so let me go ahead and use a different color here. So using these two triangles, we can say that, because they're similar, we can say that 6 is to 9 as 3 is to y. So let's use that. 6 is to 9 as 3 is to y. And that'll help us solve for y. So we get cross multiply, you get 6y equals 27, which means y is let's see here, y is going to be 4.5. So now we know that that's 4.5, and we already knew that x was 7.5. So we can subtract that to get z. So z is going to be 7.5 minus the 4.5, which is 3.0. And there you go. That's how we get z or wz. So the answer is A. All right, so there's a lot of similar triangles that we used to get that. I'm sure there's another way to do it, but that's the way that I thought of it. The way I just thought of it at the moment. So for number 4, you got SU and RT bisect each other. Select all the theorems that can be used to show that RSV is congruent to TUV. So let's go ahead and draw RSV and TUV. So we got R, S, V. V is like where they intersect, and TUV. Okay, so I just got two triangles. They bisect each other, which means that they cut each other in half, and the point at where they cut each other in half is at V. So SU, let's see. So SU is all of this, by the way. It's kind of hard. It's a very bad drawing here. So SU, these cut each other in half right here, basically, at point V, and then those are my two triangles. So select all the theorems that can be used to show that they're congruent. Well, we can show that they're congruent by side, and we know that these are vertical angles, so they must be congruent. Side, angle, side. So side, angle, side works. You cannot use side, because we don't know that the third side is congruent. You don't know, you can't use angle, side, angle, because we don't know another angle on here other than the one in the middle. And we can't use angle, angle, side, because we don't know another angle other than the middle. And you can't use HL because we don't know what the hypotenuse would be or anything like that. So So we're going to be choosing this one. All right, so for number 5, what is JL? So this is a theorem known as altitude on hypotenuse theorem, or altitude to hypotenuse theorem, where you start out with a right triangle and you draw an altitude to the hypotenuse to make another right triangle there. Okay, so there's a couple of ways that you can do this. Let's list out the triangles that are congruent. So we know that triangle JKL is similar to triangle KML. So JKL is this one, that's the right angle one, and that's similar to triangle KML. That's this one right here, because we got our right angle there, and they share this angle. So because they share that angle, I know that has to be congruent to itself. And so angle L is congruent to angle L. And so let me draw this in purple. And they're all similar to triangle JMK. JMK is this one right here. This one has the right angle here. And let's see here, JMK, and we know that angle J is congruent to angle J for this blue one. They share that same angle. And this angle here is congruent to this angle J. Angle K is actually equal to angle K on the red one is congruent to angle L on the other ones. Okay, so those are all similar. So hopefully you're able to kind of spot, that that's the case. So because we can do that, because we know that that's true now, we can set up a proportion. We're going to be using these two triangles, by the way, to set up a proportion, because we're interested in solving, here we're trying to find JL, right? So we're trying to find all of this. Okay, so first off, let's call this X right here, because we want to be able to find that. So if I want to find that, then I can add 8 to it to get JL. So we know that 6 is to, here, let me get rid of all this mess here. We know that this 6 right here is to X, because we know that KM is to, oops, that's not it. We know that 6 is to not X, sorry. KM is to JM. And JM is 8. So 6 is to 8, not X. And then we got 6 is to 8 as X. X is ML, by the way. So ML is to MK. And MK is 6. 6. So there you go. So 6 is to 8 as X is to 6. I know that can be a little confusing. I highly suggest maybe drawing the triangles separately and then figuring it out that way. But just for the sake of time, I'm going to leave it at that. Okay, so using the similarity statement. So now you can cross multiply, and you get that 8x is equal to 36, then divide by 8 on both sides to get x. So bottom line is x is 4.5, and so therefore JL has to be 8 plus 4.5 or 12.5. And there's your guy. So another way to do this is by using the idea of geometric means. So we know that for the altitude on hypotenuse theorem, that in order to find the this altitude here, this altitude is always going to be the geometric mean of the two sides that you split it into. So we can also use the fact of geometric means, that 6 is the geometric mean of 8 and x. And we know that to find the geometric mean, you take the square root of the product. So it's going to be square root of 8 times x. And if you did that, you get 36 is equal to 8x, which is exactly what we got here. Okay, so that's another way that you can do it in terms of geometric means. All right, so for number 6, so it says write a proportion that you can use to find the value of A, then find the value. So So we're just using proportions like we did before. This time I'm going to show you how to do this by drawing it out. You know, unlike the other problem where I didn't draw it out, I'm going to draw the two separate triangles here. So let's look at this one, this triangle here, and we want to compare that. So let's do the original. The original one, let's call this X, let's call this Y. And let's go ahead and draw out this original big one. And so that big one is going to be X, A, and 18. Okay, then let's draw the smaller triangle, this one right here. Okay, so first off, since this side is equal to 16 and the whole thing is equal to 8, I know that this is equal to 2. So I'm just going to label that 2 right now. Now, if I want to compare that to the big one, how do I do that? Well, if I take this red triangle and I kind of flip it this way, right? I get something that kind of looks like that. And then I can rotate it. Then I can get it in line so that it looks like the blue. Okay, that's exactly what I'm going to do now. And so this 2 goes here and then goes here if I rotate it. And this X goes down here, and this Y goes, actually looks like it's going, actually this is going to be Y, sorry. And then this X kind of flipped and became kind of like the hypotenuse right there. Okay, so 2y and then x. And so that's what I'm going to do. That's my smaller triangle. My smaller triangle is 2y and then x. Okay, so there's my two triangles. And then we can write a proportion to solve for a. Okay, so we know now that from this, oh, there's one more triangle I forgot to draw. So let's draw the other triangle. So this one right here, this green one. So for this green one, we know that the right angle is actually here. So how do I compare this green one to the big blue one? Well, if I think about it as, say, you know, kind of flipping it, right? So let me get rid of this red mark here. If I think of it as like flipping it, then it's going to look kind of like that. And then I can rotate it. Then you can kind of see that it'll hopefully look like, you know, a triangle that we can compare to the blue one. Okay, so if I kind of rotate it this way, you can kind of see that this will go down like this, and then that this green side here goes downward. Okay, and so if we were to draw it, then it would be this side is going to be y, because the y here flipped and became the y there. Okay, and this bottom side is going to be 16, because this 16 that was here flipped down here, right? So that's 16, and then the other one is going to be a, which is that top side, because this is a right here. Okay, so hopefully I convinced you with rotations and all that stuff that that's true. So those are my three triangles. Now let's go ahead and use those triangles to find a. Let me erase all this mess here. Okay, so if I wanted to get a, I can use this one and these two, because those two have a in them. So let's use the blue and the green. So a is to 16 as 18 is to a. And there's my relationship there. I can cross multiply. I get a squared equals 16 times 8, which is 288. And then I can take the square root of both sides to solve for a. So a is equal to square root of 288, which I can break down into 144 times 2. The square root of 144 is 12. So there's my a. Okay, there's a lot going on there, and it's actually harder than it looks, right? So I would say practice drawing those triangles to establish similarity. Okay, so number 3, to find the height of a lamppost at a park, Rachel placed a mirror on the ground 20 feet from the base of the lamppost. She then stepped back 4 feet so she could see the top of the lamppost in the center of the mirror. Rachel's eyes are 5 feet 6 inches above the ground. So this is the same thing as 5.5 feet, because 6 inches is half of a foot. What is the height in feet of the lamppost? Okay, so she's roughly 5.5 feet tall, basically to her eyes. And she's standing a distance, it says, of 4 feet away, right? So it says, yeah, she's standing 4 feet away. And we want to figure out how tall the lamppost is. So you can see that this is a right triangle, this is a right triangle, they're similar to each other. And it says that the mirror is 20 feet from the lamppost, so it's 20 feet from the base. So we have all we need to solve for h. So we can see that h is to 5.5 feet as 20 is to 4. So we get 20 divided by 4 is 5. So h is to 5.5. We can just cross multiply, actually. Let's do that. We cross multiply, we get 4h equals 20 times 5.5. Then we'll divide by 4 on both sides. And we get h is equal to, do that on the calculator real quick. Get h is 27.5 feet. Okay, so we got next standard. Understand that by similarity, side ratios in right triangles are properties of the angles of a triangle leading to trigonometric ratios. So this is about trigonometry. So for number 1, it says, what is the exact value of tangent of A? So you just have to know what tangents, remember SOHCAHTOA. You just got to remember basic SOHCAHTOA here. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we want to figure out A. So this is going to be the opposite side, directly opposite of the angle. This is adjacent, this is hypotenuse. So tangent of A is equal to opposite over adjacent. So the opposite side over the adjacent side, which is 9. There you go. That's it. So for number 2, what is the sine ratio of angle P in the triangle? So this time we're looking for this guy. This has to be opposite. This is hypotenuse. Remember SOHCAHTOA, you want to look for sine, which is opposite over hypotenuse. So the sine of angle P is equal to opposite over hypotenuse. And there you go. Simple as that. So for number 3, what is the cosine ratio of z? So we want to figure out that. This is opposite, this is hypotenuse, this is adjacent. Notice that cosine is SOHCAHTOA, so you need adjacent and hypotenuse. How do I get the hypotenuse? Well, I need to use the Pythagorean Theorem. 12 squared plus 16 squared equals hypotenuse squared. Let's do that first. So we take the square root of both sides to get the hypotenuse. So the hypotenuse is going to be square root of 400 or 20. There you go. So this is 20. So now we can use SOHCAHTOA. Cosine of z is equal to a over h. So ca 12 over 20. We go ahead and reduce it, divide by 4 top and bottom to get 3/5. All right, so for number 4, say what is the perimeter of the triangle to the nearest tenth? So we need to figure out, this is x, let's call that y. So if I want to figure out x, I need to use trigonometry. So I know that this is the opposite side, this is the hypotenuse, and this is the adjacent. So let's use some trigonometry to find out what x is. I need a and h, so that's cosine. So cosine of 38 is equal to a over h, and h is 18. Multiply by 18 on both sides to solve for x. Then you can get that as a decimal. So 18 cosine of 38 degrees is equal to approximately 14.2. All right, so now let's go ahead and solve for y. We know that y is opposite, so we have opposite over hypotenuse. So that's going to be sine. Sine of 38 is opposite over hypotenuse. Then we can multiply by 18 to solve for y. And so y is approximately, you can plug that in the calculator. Y is about 11.1. And so then we can add up you can find the perimeter by adding up all the sides, 11.1, 14.2, and 18. And so the perimeter is 43.3. All right, so for number 5, complete the diagram given. So we want to find sine of A. So we want to do opposite over hypotenuse, and that's going to be sine of A. So sine of A is opposite, which is 9, over hypotenuse, which is 3 square root of 13. Now it's essential. We know that 9 divided by 3 is 3, by the way. So we get 3 over square root of 13. It's essential that you rationalize the denominator. To rationalize the denominator, you multiply top and bottom by that same radical. So we got 3 times square root of 13. Now square root of 13 times square root of 13, these square roots cancel, leaving you with 13. Okay, so let's do cosine of A. So this one's going to be adjacent. So it's going to be 6 over 3 square root of 13. We know that 6 divided by 3 is 2. So this becomes 2 over square root of 13. Multiply top and bottom by square root of 13 to rationalize. And you get 2 square root of 13 over 13. And then finally, we'll do tangent of A. So tangent is TOA, SOHCA TOA, opposite over adjacent. So it's 9 over 6. Reduce that, divide that by 3 top and bottom to get 3 over 2. And there you go. That takes care of number 5. All right, so let's look at the next standard. Explain and use relationships between sine and cosine of complementary angles. All right, so let's solve for m for this. We need to know the relationship between sine and cosine, which is part of the standard. The relationship between sine and cosine is that sine of an angle, so let's say sine of x, for instance, is always equal to cosine of 90 minus x. In addition, cosine of x is also equal to sine of 90 minus x. So basically saying that if I know cosine of 30, then that means that's the same thing as sine of 60. If I know the sine of 30, then that means I know the cosine of 60, right? Sine of 30 is equal to cosine of 60. And that's because these are complementary functions. They're complementary angles. 30 and 60 are complementary. CO for cosine stands for complementary sine. So they're complementary to each other. Okay, so in order to solve this, I need to use that complementary relationship. So let's go ahead and say that for the sine, let's go ahead and replace that and say that that is the same thing as cosine of 90 minus the angle, right? That's the angle right there. So 90 minus that, and then the cosine of that is equal to the sine of the original. So let's put this away. This is equal to the cosine of 7m plus 2. And there's my equation, okay? So I want to solve that equation. Obviously, these cancel out because they're both cosines on either side. So we can say that this is equal to that. So we get 90 minus all of this, 18 minus 12, equals 7m plus 2. We solve that next. Distribute the minus sign there, so 90 minus 12. This is a double negative, so this actually becomes a plus. So 90 plus 12 is 102. And then we got minus 18m equals 7m plus 2. We'll subtract 7m on both sides, or actually we'll add 18m on both sides. And then we'll subtract 2 on both sides. So we get 100 is equal to 25m, which means m is 4. Divide both sides by 25. All right, so now we talked about the relationship between sine and cosine. Let's see if we can use it here. The figure shows right triangle ABC of the listed values which are equal to the sine of B. Select all that apply. All right, so sine of B. Well, sine of B is opposite over hypotenuse, so it's going to be B over A, right? So sine of B is B over A, so that's good. It's definitely not equal to C over A or B over C, so I'm going to cross those out. Is it equal to the cosine of B? Well, no. The sine of B, right, is equal to the cosine of 90 minus b. Okay, so keep that in mind. So is equal to the cosine of 90 minus b. Now, 90 minus b is this angle right here. Like if this is 90 and this were 30, then this has to be 60, right? 90 minus 30 is 60. So basically, sine of b is the same thing as the cosine of c. Okay, so this is the same thing as the cosine of c. So yes, that is true. It's not the same thing as cosine of b though. Is it equal to the sine of 90 minus c? Well, let's take a look at that. Well, if c is 60 degrees, 90 minus 60 is 30. So that means that the sine of 30 is equal to the sine of 60 minus, or 90 minus 60. So this is true. Okay, so that takes care of that question. For the next one, explain why cosine of x is equal to sine of 90 minus x, such that x is between 0 and 90. So we're going to show this with an example. Okay, so let's say I had a right triangle. And let's call this A with sides A, B, and C. And let's call this angle X, okay? And if that's X, then this angle right here, then this angle on top has to be 90 minus X, right? This angle on top has to be 90 minus X. So if this X were 30, then this one on top would be 60, right? For 30, 60, 90. Okay, so this is our setup. Now we know that cosine of X, this is opposite, this is hypotenuse, this is adjacent, right? So cosine is adjacent over hypotenuse, so it's going to be little a over little c. Okay, so that's cosine. Now let's go ahead and show that sine of 90 minus x is equal to that. So sine of 90 minus x, so the sine, now this time we're looking at this angle, right? So the opposite of that is a, the hypotenuse is still going to be c. So notice that I still get little a over little c, and therefore these are equal to each other, and therefore we kind of showed that this is true. Okay, so cosine of x is equal to sine of 90 minus x. Okay, so for number 4, Adnan states if cosine of 30 is equal to that, sine of 30 is equal to that, or if cosine of 30 is 0.866, then that must mean that sine of 30 is 0.866. Which justification correctly explains whether or not he is correct? Well, we know that it's not equal to 0.866, that sine of 30 is not equal to 0.866. Remember that cosine of 30 is the same thing as sine of 90 minus 30. Remember that complementary relationship? So cosine of 30 is actually equal to sine of 60, not sine of 30. So that 30 is wrong. So therefore, this should be 60. Okay, so Adnan is incorrect because cosine of x and sine of 90 minus x are equivalent. Okay, so it's going to be C. All right, so the next standard is use trig ratios in the Pythagorean theorem to solve right triangles. So Jack's eyes are 5 foot above the ground. So here's Jack, and we'll say that his approximate height is 5 feet. He is standing 400 feet from the base of a building, I guess. The angle of elevation of his line of sight to the top of the building. So that's his line of sight. The angle is 67 degrees from that flat horizontal line to his eye line. How tall is the building? Okay, so this is going to be, let's call that X. And let's call the height of the building H, right? So obviously to get H, right, I need to get X here, and I need to add in this height. H is equal to X plus whatever this height is. But we know that that's the height of Jack, and Jack is 5 feet. So H is going to be X plus 5 feet. So if we find X, we find H. So let's go ahead and focus on finding X. Notice that this is a right triangle right here, right? So we can solve this right triangle. So let's do that, and let's plug that in for X afterwards. So we know that this is 400 feet for this bottom side. So I'm going to label it as such. Hold on a second. So this has to be 400 feet. So we can use a trig function here. This is opposite, and this is adjacent. So we're going to be using a tangent. So tangent of 67 degrees equals opposite over adjacent. Remember SOHCAHTOA. Multiply both sides by 400 to get x. So x is approximately, if we calculate that, x is approximately 942.3 feet. And then we can go ahead and plug it in here to get h. So h is 947.3 feet. So that's going to be D. Okay, so number 2. Garrett makes a ramp for his skateboard in the shape of a right triangle with a hypotenuse of 2 feet and a leg of 1 foot. He wants to use a trig ratio to describe the relationship between these two sides. Select all the expressions he could use. Okay, so basically for this triangle here, this is actually a 30, 60, 90 triangle, because we know that for a 30, 60, 90 triangle, if the hypotenuse is a certain number, then one of the legs is always half of the hypotenuse. And that's the case here, that 1 is half of 2. So this has to be 60 degrees, this has to be 30 degrees, okay? That's for a 30, 60, 90 triangle. The shortest side is always half of the hypotenuse. And the shortest side is always next to the 60-degree angle. So once you realize that, this question becomes easier. To figure out, it says if you want to use a trig ratio to express the relationship between the two legs here, 2 and 1, well, that's going to be adjacent and hypotenuse, right? So if you were to do 1 over 2, that's going to be cosine of 60 degrees here. So we're going to go ahead and check cosine of 60. But remember that it's also equal to sine of 30. So if I do sine of 30, that gives me opposite, which is 1, over hypotenuse, which is 2. So it's also equal to the sine of 30. And those are my 2 answers. Okay, so for number 3, Michaela is shooting a paintball gun at a target in a tree. Michaela is at point G, and the target is at point E. So, okay, so this is where Michaela is, at point G. Assuming her paintball shoots straight, what angle should she aim at? So this angle here, what angle should she aim at? Let's call that theta, in order to hit the target, and the target is up here. Okay, so basically we have opposite over adjacent. That's a tangent. So tangent of theta equals opposite over adjacent. And in order to solve for the angle, I need to use the inverse tangent. I need to get rid of this tangent. The only way I can get rid of that tangent is by doing an inverse tangent. And that will cancel it out. Whatever I do on one side, I got to do on the other side. So I know that theta is equal to the inverse tan. I can type that in the calculator, and if I did that, I would get 31.6 degrees. Okay, so for number 4, the angle of elevation from a viewer to the top of a building is 50 degrees. The viewer's eyes are 5.5 feet above the ground. So that means that this distance is 5.5 feet. And the viewer is 80 feet away. So this is a right triangle. We want to figure out the height of the building. So we're trying to figure out that height. But we know that that height is equal to this height here, which I'll call x, plus this height here, which is 5.5, the viewer's height. And so let's go ahead and focus on finding this x here from that right triangle. So that's going to be opposite over, this is 80 down here, adjacent. So we're going to use a tangent. So tangent of 50 degrees is opposite over adjacent. Then we'll multiply by 80 on both sides to get x. And doing that on the calculator, x is approximately 95.3 feet. And so we can plug that in here. And so the height is that plus 5.5, which is 100.8 feet high. All right, so for number 5, a 30-foot long escalator forms a 41-degree angle at the second floor. What is the closest height of the first floor? So we want to figure out that height. Let's call it h. So that's going to be, so this is opposite, this is adjacent, this is hypotenuse. So a and h. that's cosine. So cosine of 41 is A, which is lowercase h, over capital H, which is 30 feet. Multiply both sides by 30 to get your height. And so the height on the calculator is approximately 22.6 feet. And so we're going to select B. For number 6, the picture shows a hamster sliding down a ramp. What is the distance that the hamster has to travel from point A to point C? So basically, we're trying to find the hypotenuse. Let's call that x. All right. So in order to do that, we need to know the opposite. And this is hypotenuse, right? So this is going to be sine, which is opposite over hypotenuse. So the sine of 40 is equal to opposite over hypotenuse. And we'll solve for x, which is the distance. So if we were to solve for x, then we can basically swap these two answers here. And I get x is 15 over sine of 40. And there you go. There's one of my responses is 15 over sine of 40. Now remember that there's two other functions. There's sine, cosine, and tangent, and there's three other functions known as cosecant, secant, and cotangent. Now the cosecant is 1 over sine. So cosecant is equal to 1 over sine. Secant is 1 over cosine, and cotangent is 1 over tangent. So if I want to do, I notice that this, if the sine is on the bottom, that's the same thing as a cosecant. So this here is the same thing as 15. Replace that with cosecant because it's on the bottom. So that's the answer right here, 15 cosecant of 40. This one was a little tricky because I honestly didn't think that they would include cosecant, secant, and cotangent in one of the questions, but they did, and so I wanted to go over that just in case. Okay, so the diagram below shows a ramp connecting the ground to a loading platform 4.5 feet above the ground. The ramp measures 11.75 feet. Determine and state to the nearest degree the angle of elevation. This is the angle of elevation. Let's call that theta. This is opposite over hypotenuse, which is going to be a sine. So sine of theta equals opposite over hypotenuse. Remember that the only way that we can get rid of a sine is with an inverse sine. So we're going to do the inverse sine on both sides. So doing this on the calculator, you get theta is approximately 23 degrees. Okay, so we got a couple of pages left, so let's go ahead and get through this. We have the next standard, prove that all circles are similar. So what is the ratio of the length of JK to arc MN? So JK to MN. So those are arc lengths. So the arc length formula is S is equal to R theta, where theta is in radians, okay? So that's just a formula you have to know. So the arc length here for JK is the radius times the angle. So it's going to be A times theta. And the arc length for MN is the radius, which is B over theta. Okay, so we're going to do the ratio of the two. So we're going to put the JK on top, the MN on the bottom. So the ratio of JK to MN, which is A theta divided by B. Oh, sorry, I put B divided by theta. It should be B times theta. Sorry about that. So it's going to be A theta over B theta. Notice that the thetas cancel out, so you get A over B. And that's all they wanted. So which statement is true for any two circles? So for any two circles, the ratio of the areas of the circles is the same as the ratio of their radii. Let's see if that's true. So let's look at two circles here. So remember that the area is pi r squared. Okay, so if I took the area of circle 1 divided by area of circle 2, well, I get pi r squared 1. This is the radius of circle 1 over pi times the radius of circle 2 squared. The pi's cancel, leaving me with radius squared over radius squared. So it's not the same as the ratio of the radii. It's the same as the ratio of the radii squared. Okay, so that's not it. The ratio of the circumferences is the same as the ratio of their radii. Let's see. The circumference formula is 2 pi times r. So circumference 1 divided by circumference 2. Circumference 1 is 2 pi times r1, radius 1, divided by 2 pi times radius 2. The 2 pi's cancel, so you get the ratio of their radii. So it's not the ratio of the, oh, it does say the ratio of the circumferences is the same as the ratio of their radii. And that is true. So we're going to end it there. Okay, so for number 3, which can be accomplished using a sequence of similarity transformations? Okay, so basically it says, can we map circle O onto circle P so that O1 matches P1? And the answer is yes, we can do that. We can take O and move it to P1, to P, right? So that it looks like that. And then that would be O1 right here. And then we can do a reflection so that we can reflect it over here. And then we can kind of shrink it, right? If we shrink it, then it'll line up with P1. So yes, we can do that. Can we map circle P onto circle O so that P1 matches O1? And the answer is yes, we could do the same thing. We can move it, reflect it, and then shrink it, and then instead stretch it. So it's because it's going to need to be stretched. So yes, we can do a similarity transformation, so it's going to be both of them. All right, so for number 4, which statement explains why all circles are similar? And here is the reason why. Let's go ahead and look at it. There are 360 degrees in every circle. The answer is no, that's not the reason. There are 360 degrees in every circle, but that does not explain why circles are similar. Remember, for any two things to be similar, the sides have to be proportional, right? There has to be a scale factor, right? So if we look at part B, the ratio of the circumference of a circle to its diameter is the same for every circle. The answer to that is, or the reason for that, when that is true, is that if my radius is 5, then my circumference must be 10 pi. If my radius of my circle is 4, then my circumference must be 8 pi. All right, so the ratio of the circumference to the radius of a circle, or to the diameter rather. So if this diameter is 10, right, 5 and 5, then the circumference is 10 pi. If this diameter is 8, 4 and 4, then the circumference must be 8 pi. So the circumference to the diameter is actually equal to pi. That is the definition of pi, by the way, is the pi is the constant, which is the ratio of the circumference to its diameter. And because this is the case, that means I can say that C1 over D1 is equal to C2 over D2. These are proportional. The proportions of this circumference to diameter is proportional to this one. And that's what we call similarity, okay? So because you have a scale factor. So that is the reason why circles are similar. Okay, so let's move on to the next page. We got this page and we got this one more page. We're going to try to get through these as quickly as possible because this video is a little long. So identify and describe relationships among radii and chords and so on, central angles, all that stuff. So this is all about circles. If angle C is 55 degrees, then what is angle D? Well, notice that this is called an inscribed angle, and the arc for this inscribed angle is this guy right here. And if you look at angle D, it has the exact same arc, which means that angle D must be equal to the same as angle C. Done. What is RS? So for number 2 here. Okay, so let's look at it. So let's call RS, let's call it X. Let's call this side right here X, okay? So there's a theorem that states that if you have that the product of any two, the product of the outside portion of a secant with the total is equal to the product of the other side, right? So if I multiply the outside portion, which is 7, times the entire length of the segment, which is 7 plus x, by the way, then that's going to be equal to, if I multiply this outer part on the other for the other segment times the whole thing. But we know that the whole thing is 11, so it's really just 11 times 11. Okay, so there's my equation. The products must be constant between these two segments. So that's my theorem. Let's distribute. 11 times 11 is 121. And then we can solve for x. I'm just going to skip forward to the answer. You can solve this very easily. Answer is 10.3 approximately. All right, so for number 3, what is angle QPS? So we're looking for that angle. There's a theorem that states that opposite angles in an inscribed quadrilateral add up to 180. So these two opposite angles, Q and S, must add up to 180. So we're going to do that first and solve for x. So 3x and 5x is 8x. 8 and 4 is 12. And if we solve for x there really quickly, we get x is 21. Then we can plug in 21 into here. So 6 times 21 minus 14. And that is equal to 112 degrees. And so with the 112 and this angle must add up to 180. So let's call this x. So x plus, or let's call it y because we already have x. So y plus 112 equals 180. So y must be 68 degrees. And so there's my answer. Okay, so Nadim is constructing a tangent to a circle Q that passes through A. What should he do next? Okay, so if you have a circle and you want to draw a tangent at a point, right, to the circle that crosses this point. Well, first off, you have to connect these two lines right here, and then call that, label that point B, for instance, here. Then you need to construct a tangent to that circle. And then once you draw the tangent, there's one step I missed. Then you want to draw this big circle that crosses that point that you want to do the tangent to. Then you're going to draw the tangent, and then you're going to label, you're going to figure out where the tangent crosses the circle, and then you're going to draw a line from Q to that point, and then you're going to label this point right here on the circle, and then you can draw the tangent. So there's a lot of steps that goes on, but basically what you got to do is the next step to this is drawing the tangent to B. So we're going to draw that, which means that we got to draw a line that is perpendicular to this radius that crosses through B. So we want to construct a line perpendicular to QA, right? Perpendicular, and that passes through B. So that's the next step. All right, so number 5, and for number 4, you have to know those steps. If you don't know those steps, then I would go back and go back to the steps of constructions. So for number 5, WP and KZ intersect at point L in the figure shown. All right, so intersecting chords. If you have two chords that intersect inside a circle, the product of the two sides of the chords are constant. Okay, so 5 times x is equal to 2 times 3x minus 2, and it's as simple as that. Then you solve it. So distribute, and then solve for x. So you get x is equal to 4. If you want to get kz, then you plug in x into here. So you get 3 times 4 minus 2. That's 10. 10 plus 2 is 12. So your answer is D, 12. Okay, so for number 6, what is the value of A? We've done this problem before. We've done it actually over for number 2. We did this over here. Okay, so to solve this problem, you're going to do the outside portion times the whole thing, which is 17, is equal to the outside portion times the whole thing, which is 4 plus A. So 5 times 17 equals 4 times 4 plus A. Distribute and solve. 5 times 17 is 85. So 85 is equal to 16 plus 4A. I'll go ahead and go straight to the answer. A is 17.25. All right, and we're in the last page, which is only 4 questions. So let's go ahead and do it. Finish up this part. So quadrilateral is inscribed in a circle in the diagram. So A is equal to 85, D is 80. Let's go ahead and find angle B. Well, we know that in an inscribed quadrilateral, the angles have to add up to 180, so this has to be 100 degrees. 100 plus 80 is 180. Done. Number 2, find the perimeter of the triangle given that the distance is 12, 16, and 8. So this is pretty straightforward. This is called the secants to a secants to a tangent theorem, something like that. I forgot what it's called, or tangent to a point. There's a theorem that states that if you have two tangents, right, that meet at a point, then those tangents must be the same length. So that's exactly what we're going to do. So this must be the same length as that. This is the same length as that. This is the same length as that. If that's 8, then this is 8. If this is 12, then this is 12, right? And they told us that. And if this is 12 and this is 16, then this must be 4, right? And if that's 4, then this is 4. So there you go. So we can find the perimeter. Add up all the sides. 4 plus, we know that this is 16. So 16 plus 12 plus 8 is 20. And then 4 plus 8 is 12. Add those all up to get your perimeter, which is 48 centimeters. Done. All right, so number 3. The center of an inscribed circle of a triangle has been established. Which point on the sides of a triangle should be chosen to set the width of the compass? Okay, so for this here, we have a inscribed triangle, a circle of a triangle. So let's draw a triangle, and this is my inscribed circle. Okay, an inscribed circle touches the triangle only at one point on each side. So if you have an inscribed triangle inside inscribed circle inside a triangle, this is the center of that triangle is known as the incenter. Now I'll go ahead and go over what you need to know for this. This is called special segments, or special segments to a triangle. These are called centers of concurrency. And the acronym that you need to remember is my cousin always owes Anna banana ice cream, probably before Christmas. So this is median, and C stands for centroid. This is altitude, and that's orthocenter. This is angle bisector, and that's incenter. This is perpendicular bisector, and this is circumcenter. Okay, so bottom line, we're looking at incenter here, which is angle bisector. Okay, so you have to construct some angle bisectors here. You have to construct angle bisectors from here to there, from here to there, from here to there, because of this, angle bisectors. So the answer is so let's go ahead and answer the question. So which point on one of the sides of a triangle should be chosen to set the width? So in order to construct this, you need angle bisectors. However, in order to choose a point on the triangle that crosses the circle, you need to do the radius from the circle to that point. And that radius is always perpendicular to this tangent line. So the answer is the intersection of the side and the perpendicular that passes through the center. And the perpendicular that passes through the center is this one right here that I circled. So it's going to be C. All right. Remember, the main concept here is that a tangent is always perpendicular to its radius, and that's why we need that. Number 4 is going to use a lot of this concept here. So number 4 says, which statement is valid when a circumscribed circle of an obtuse triangle is constructed? Okay, so circumscribed means circumcenter. Circumcenter means perpendicular bisector. So if I got a obtuse triangle, which is what we have here, an obtuse triangle, let's draw an obtuse triangle. That's an obtuse triangle because that's an obtuse angle there. So circumcenters are formed from perpendicular bisectors. So the perpendicular bisector of this side is this guy, cuts it in half at a 90-degree angle. The perpendicular bisector of this side here cuts it at a 90-degree angle in half there. And then finally, the perpendicular bisector of this here is over here where it cuts this at a 90-degree angle. Cut it in half. Notice that they meet here, and that's known as your circumcenter. And so that circumcenter makes a circumscribed circle. It's the center of a circumscribed circle. The circle is always the same distance from each of the corners of the triangle. So the radius of the circle is actually the distance from the circumcenter to the vertices. And that's your circumscribed circle in red. So which statement is valid? The longest side of the triangle lies on the diameter. No, this is the longest side, and that is not the diameter of the circle. That's actually a chord. So it's not A. The circle is drawn inside the triangle, touching all three sides. No, it's not touching all three sides, and the circle is on the outside. So no. The center of the circle is in the interior of the triangle. The center of the circle, which is here, is in the interior. No, it's on the outside of the triangle. So that's not it. The vertices of the triangle lie on the circle. Yes, the vertices actually lie on the circle itself. So the answer is D. All right, guys, I know that was a lot. I hope you learned a lot of things from this video, and I hope you found it useful. As usual, I'll see you in the next one.